Hello, welcome back. Nicole Granucci here for Physics 100, Physics and Music, and this is Acoustics Part 2. In this video I'm going to talk about how geometry can actually change the reflections, so the way your room is shaped obviously can change what you hear. Then I'm going to talk about what happens when light can, or sound waves can bend, called refraction, and then I'll conclude this video with diffraction, which is the bending of waves around corners. So let's start. So I ended here just to take a step back, and in the previous video I talked all about reflections, specifically reverberations. Those are the ones that we care about because we want the room to sound more full. And of course, too much reverberation makes the sound more garbled. So you actually need to play this balancing act between clarity and articulation and fullness, intensity, meaning how loud things are, but not only how loud, but how loud the highs of those notes are and the lows of those notes are. So one way we can actually kind of change our reflections is through geometry. So if you haven't done geometry in a little while, which I assume you may not have done, and you kind of might know this already, but curved surfaces have this very special special characteristic where if you send in perfectly straight lines, so this can be light, this can be sound, and it hits a curved surface. Now this is like part of a circle, so assuming that this is all symmetric, meaning that these sides are both the same, that the curved surface actually will bounce the ray off, but it comes to a very special position or point called a focal point. You might have heard of this as a focus or a focal point, as I mentioned, but that's actually really good and bad when it comes to sound, right? You can see maybe some good qualities and bad qualities. Now, one of the good qualities is that this is good for collecting information or data. So that's why if you notice these things right here called, this is a telescope, whether it's a radio telescope where it collects radio waves or optical light waves. So it takes all the waves and kind of like this, I'll do it with my mouse, you can't really see. It takes all the rays, regardless of where they come from. If they hit this curved surface, they come to this focal point right here, which is nice, so it collects them and puts them into one spot. I don't know if you ever wondered this. I did, but if you notice the detector, it's actually not on the telescope, it's actually here, because that's where all the rays come together. So this is where the detector of the radio waves or your optical waves, depending on whatever you're studying, is actually over here, and that's why these discs, these information discs, are shaped this way. And that's why they're shaped in a bowl, so they collect them and put them in one spot. It's a great way to gather information. So early in outdoor acoustics, they use what is called like the clamshell. Actually, that's a very literal clamshell right there. But think about what that does. I mean, this is not the perfectly curved surface, but what it can do is it can take those sound waves, hit this surface, and then send them back out to the audience. Instead of getting lost, if there was no curve here, those sound waves would actually get lost in the environment. So it's a great way when you do outdoor acoustics, to be playing next to a wall, and even more, even better, a wall that has a slight curve to it like this. So many ancient societies actually have used this, quote, technology to help with, amphitheaters, they're called, or to do plays or shows or play music. Another interesting effect of curved surfaces is called the rotunda effect, also known as the whisper gallery. So this is actually pretty cool. So you can actually this is actually Grand Central. And you can really do this, and I couldn't believe this. You can actually do this in New Haven too, but what you need is a surface, if you notice, that is curved like that. And you have one person stand and face the wall right here, and you can just talk to them and say, hello. Well, the sound wave, because of the structure and the geometry, will bounce. Notice the way it bounces, it stays all around this circle like this. So you could actually whisper and talk to somebody on the other side and actually hear them. It's a really cool effect called the rotunda effect. also known as the Whisper Gallery. So there's a really cool, so I know this, so this is just a, another picture. This is actually in the textbook, interlude. I'm sorry. I'm trying to think of the chapter name. I can't think of it at the moment, but this is in the textbook, Measure Tones. But this picture I know is very boring because you really can't get the sense of what it is. But it's actually a dome. This is at Rockefeller Center, and they actually, so Rockefeller wanted to have this, like, luxury lounge for, like, stars. So many stars that perform there. I can't think of anybody's name at the moment, of course, but I'm going to make up a name because I'm not sure this is true. Let's say Elton John, okay? They have a big, like, kind of big celebrity loft where they can entertain and stuff. This room that you're seeing right here is actually dome-shaped, because he wanted everybody to hear everybody else. He didn't want to have any secrets or anything going around. So this is a dining hall, and you can see people. I took a picture of this, where it was called the the dining hall. You couldn't whisper about anybody else. You had to be able to just talk to people. So like I said, you can't get the effect at all. This is actually a round domed room, and you get this sensation. It's actually pretty cool. I took a tour of Rockefeller Center, as you noticed. This is pretty cool too. I hope this works. So this is at the Seattle Pacific Science Museum. Now what you're seeing is a big curved disc, and my lovely daughter is demonstrating what you do with it. So notice that there's this little circle. This is the focal point, and she is talking to my husband, which is, as you can see, all the way back here. Of course, I took a picture for this specifically for this class because it's pretty cool. And she's talking to him, and they can hear each other pretty well. In fact, I couldn't get over it. I actually got an audio of this, so let's see how well this works. So I hope you notice, I'll just talk over it, talk now. But I hope you notice you can hear my husband, even though he was all the way over there. I mean, it's not super loud, but you can still hear him. So he's talking from all the way over there. I'm going to play it again. Oops. I'm just going to play it again so you can hear it. Yeah, so it was a pretty cool effect. Just making another point, not really going to, emphasize this, but if you take those two curved surfaces and put them together, you get an ellipse. And in fact, because you have two curved surfaces, you actually can get two focal points. So imagine, this will actually be bad acoustically, right? Because if you didn't sit in these focal points, you actually wouldn't hear the sound. So, it's good to help bounce the sound, but not have a perfectly symmetric and acoustic, situation like this, because you actually wouldn't be able to hear the sound. You'd have to sit in focal point 1 or 2, which is not desirable. So what do? You have what is called anti-focusing surfaces. So notice instead of taking the sound waves and putting them on the inside of the curve, we put them on the outside. And they do just the opposite. Instead of sending the waves to one spot, they send them all over, as you can see here. And then what you do with that is you take them and you make these ribbed effects, so you can send sound everywhere. This, of course, is more desirable because you want to send the sound wave everywhere. And this is just talking about some of those same effects. Highly flat walls will give you perfectly reflective and give you more of an echo. Angle side helps, but if you make them into these shapes right here to allow for multiple reflections, you get a better, more diffuse sound, meaning it goes all over the place. Here, diffuse, that was our term before. This is just explaining the same thing. So you can you could read the stuff later, but if you notice, the difference between having flat walls and having curved walls is much different. Having flat walls will send them to specific locations, but this will send them, you get more likely chance to actually hear all the sound. Well, here it is again, Rockefeller Center. Like I said, I got to take a tour, which was actually totally worth it. So if you go to New York and you want something to do that's a little different, I highly recommend this. I think had low expectations for it, but I actually learned a lot, and it was actually really cool. So this is the Rockefeller Center. I think I need an A there, but that's okay. But this is really cool. Actually, there's a pipe organ down here, and all these holes are for the pipe organs, because the organs are actually inside right here. Notice the way the walls are. Not only are they clamshelled, but notice I took a picture. You can see how they're all ribbed exactly like this to help disperse the sound. So this quality of the sound is really good in this place. Just some different examples. Here's someone taking that sound effect, different angles to a great effect. I forgot the name of this, of course, on the video. I'll have to come back with that name, where this place is. I think it's in Germany. I'm so mad I forgot it. This is the Boston Symphony Hall. So this is designed with lots of wood, less carpeting, beautiful, beautiful pipe organ back here, but maximizing your your acoustic qualities for, of course, acoustic shows. Okay, so just showing you how concert halls are actually designed to be heard well. In fact, actually, I'm so mad that I forgot this. I want to see if I can quickly find this, but best concert hall in the world. They just made one. I want to see if I could find it really quick for you. Live on video here. Classic FM, I don't want that. I don't know if this... Yeah, so see, these are some, the Opera House. You've seen this before, right? Man, no, it's not what I want. Best acoustic. I'm going to try one more thing and then I won't waste your time. Acoustic concert hall in the world. Yeah. Pretty interesting, huh? New York Carnegie Hall is the best acoustic place in the world. Is this what I want? Yeah, I think this is the one. I saw it, yeah, literally last year. I have to put this in the slides. I meant to put this in the slides. Germany. The world's first acoustically perfect hall opens. This happened last year. I want to show you the picture because I think the picture is really what makes it really unique. Look at this place. Pretty weird, huh? Look at this thing. This looks like a mushroom coming out of the top here. But this, you could read the article, that I kind of Googled here. But, oh boy, that's the problem with this. You get all these pop-ups. I wanted to just show you the picture because look at the design is really the big thing here. How they made it, the reflective surfaces, the angles, everything is made for perfect acoustics. So I think that's just really cool. And this is recent. This is 2017. So just wanted to show you that there. Sorry about that. Let's go back to here. Okay, so for the rest of the video, I'm going to talk about two other features of waves. Like I said, you can spend an entire lesson on this. In fact, you're just getting the small bits of this in relation to sound. But this is huge with light. In fact, do I have it later? I'm just checking. Yeah, okay. Okay, so refraction. What does refraction mean? It's the bending of light when it hits two different media, okay? So I'm actually going to visually show you it because I think it's best to just see what's going to happen here. Okay, so what I have here is a laser, and the first media, or material is air, and then the second one is water. So watch what happens. I'm going to go ahead and use my laser here, and I hope you notice that if I do something like this, that this angle right here relative to the normal is different here. That's called refraction. So the fact that this light bent into the new medium is refraction. What you're seeing here is the law of reflection. In fact, let's verify. So you're seeing the reflected piece and the transmitted bent piece. So just to be dramatic here, I have this pretty close to the 98. It's not going to be perfect because I'm doing this with a mouse. But notice if I put this at 60 here, the incident light or the incoming light equals the outgoing reflected light, 60 here. Let's be dramatic. Let's go to 30. Notice that 30 matches 30. That's the law of reflection. Just ignoring, of course, the bottom piece right here, just this piece here. Now, refraction is the fact that, notice if I go from, my top here, my angle from this point here, 0 to here is 30. Notice that that's not the same. From 0 to about, it looks like 20 here. I'm just going to estimate. They're not the same. Because they're not the same, that's called refraction. Now, refraction only happens if you're not perpendicular, meaning perfectly straight up and down. Notice that the light does not get bent. But as soon as I start doing this 10-degree mark from here to here does not match this 10-degree mark. That's refraction. In fact, the more I do this, the more elaborate. So notice at the 60 mark here, I'm not even close to 60. I'm only at like 40 here, it looks like. So that's refraction. So refraction changes based on the medium. So if I make this denser, notice I get more bending, right? So if I went to water to like honey, syrup, something denser, glass, diamond, you get more of a bend, and you get less of a bend when it's similar. In fact, if it's both the same, you don't get any bend, air and so this is a measure of the refractive index, how much it bends, so 1 and 1. If they're the same, air and air, they're not going to bend. But as soon as you start changing these two numbers, that is refraction. If you've taken physics before, this is Snell's law, which you will do in lab as well. I'm not going to introduce Snell's law at the moment. It basically says that there's a ratio between the material and the angle is equal to the outgoing angle and material. That's Snell's law in a nutshell. Okay. So this is just an interesting view. This is from one of the textbooks. But if you have, this is so old, right? This is actually an old-fashioned lawnmower machine. So this is the one that actually you cut with the 2 blades or 4 blades. I don't even know how they work. And they start off on a sidewalk and say it's rolling on its own and it gets the grass, it slows down, and because it slows down it kind of bends. I don't know if that was helpful, but that's what this diagram is supposed to show. The more dense you get, the more bending you get. And also, as you might imagine, the more dense something is, the harder it is to move through. You actually slow down. So light and sound slows down when you go into more dense medium. So air going into water, sound waves coming from air and going into water will actually bend and slow down. How does this apply with sound? So here's an example. We have warm. So this can happen where you have a hot day, like pavement over time gets really warm. Now the pavement will warm the air just above it. You can actually feel it if you've ever done it before, right? Like a hot day, you can feel the air above the pavement is really hot. And then as you go further off, it's a lot cooler. So what it means is that because of the way this happens, you get a curve of the sound wave. So here's a case if you're playing the trumpet next to a hot, surface, the air might curve up. And even though this dog is directly in the way, the curving or the refraction of that sound wave will actually go away. So this is if you are on a driveway. So you could be actually calling somebody and that sound wave might miss them because of the curving, the refraction. Or vice versa. You can have something like another example, a cool air could be like a lake. So generally the air of water, like a body of water, the air above a body of water is cooler than, as you get further out. So the water wave can actually the sound wave can actually curve down. So here's the case of the dog actually hearing that sound because it curved toward him instead of away. So sound carries over bodies of water well. So if you're going to camp, on one side of a body of water and you play music, that would actually curve perfectly well over here, which is good and bad. If you're sharing campsites, maybe you want to be a little more quiet because that sound will carry over quite nicely. Or you're trying to talk to somebody, it's going to be a lot easier to talk to those people. This same effect works for mirages. Now I'm just deviating slightly from our topic of sound and talking about light, but I always wondered why it looks like there's water, right? Or it looks like a mirror. Well, it's kind of the same idea. What happens is that the light waves get bent and they look like a reflection. So because they get bent, they look like law of reflection works. So notice the in becomes the out exactly the same at that one spot. If you ever notice, mirages or this effect only occurs in certain spots. It doesn't occur everywhere. It's like a sweet spot. So it has to have this specific distance, but you can get the sensation of glass or water of this. And this also comes from refraction back to, notice the warmer air curves up. Warm air curves up, cold air curves down. That's all you really need to know from this. Again, I'm going a little more into light, not sound, but just to mention it because it is kind of important. This is how your glasses work. Your glasses take light and bends those rays to a focal point, or takes those rays and expands them out. In fact, generally, a diverging lens versus a converging lens, so this is converging versus diverging, I can actually tell what kind of prescription you have based on your glasses. Usually, if you're farsighted, you have a converging lens, and if you're nearsighted, you have a diverging lens. I'm nearsighted, so I have a diverging lens. But anyway, this is another application of refraction, which you will study in lab, but not, in this lecture. Finally, we'll talk about the last topic, which is called diffraction. So it turns out waves can bend around corners. So I'm going to use this. Do I have it? Okay. I'm going to use this quickly as a visual. But if you think about it, if you have like particles, just like, I don't know, not a wave, and you block it, you get this distinct, right? This distinct line from where you are blocked. But sound waves don't work that way. Sound waves, actually, if you notice right here, curve around. And they make, instead of the straight line we would normally see, they actually do this. This is a property of waves specifically in the bending of around corners. Now, intensity is definitely stronger in front. Notice that it's easier to distinct a wave right in front of it. And you can see that here and here. The wave is easily distinguishable right here. But as you go out, it kind of fades. So you would naturally hear a louder sound here, and then as you go out, softer. But basically, sound waves do this. So I'm actually going to skip these for now. Fine, I'll do it. So turns out that if you bought a concert ticket and you, for some odd reason, got it behind a post, which no one would ever do, but let's say maybe you do, you'll actually still get some of the sound quality. Now you won't see anything because that's a small wave and that blocks it, but strangely enough you will be able to hear it, despite the fact that there's an obstacle there. And more importantly, if you're going to get refreshments or food or whatever, I'm thinking of, I don't know, the Meadows, or Comcast, I don't know what it's called anymore in Hartford, you could actually still hear the sound because the sound will travel around the corner. Another application of diffraction is low notes. So because low notes are bigger waves, they're less likely to get blocked by other obstacles versus small waves. So if you're in a marching band, what you're going to hear is actually the big bass and drums first. And then you'll hear the trumpets or something like that. But they're directional, so unless you're standing right in the line of these instruments, you probably won't hear them very well. Now, they still bend, but the point is you're going to hear bigger bass more and easier first than the small waves like this. The bigger waves spread out and can go around obstacles. So this is kind of what it's saying here, that the big waves have an easier time going around obstacles versus smaller waves. This is why, of course, we can hear around corners. So if I have the door open, I might still, even though you're around the, I'm looking at a physical door here, not that you can see that, but if you're standing outside of this door and I'm inside this room, I can still hear you, or vice versa. This is due to diffraction. So another couple of interesting features of diffraction include so loudspeakers, of course, you know, when you have a really loud speaker, the lower notes kind of spread out better. You can hear the thump and the bass more than you'll hear the high parts as you go around corners. Fun fact, if you're ever on Jeopardy, owls' hoots are low so that they travel further. So you can hear an owl hoot in the forest better than a small sparrow because of the frequency. And that's on purpose so that they can communicate and then they can talk to one another. Then lastly, thunder can be heard for miles. It's such a low sound. So the lower frequencies travel better and diffract better than high frequency sounds. Okay, so this is some of the resources you can look at in terms of if you need some more information, including our optional textbook right here. And just to summarize this lesson, so as you can see, it gets really complicated quickly when it comes down to talking about how waves interact with their environment. So reflection is big in sound because it actually can help us enhance or reduce you know, clarity of sound. Geometry is a big factor in how you can change your sound waves. Sound waves can be refracted. Specifically for sound, it's all about temperature. So, you know, looking at, you know, the pavement versus a body of water can actually shift, or not shift, that's a bad word, bend the sound waves. That's called refraction. And diffraction allows you to hear sound around corners. This is a wave property. So that means actually light bends around corners too. You kind of know that. I mean, the effect is much smaller than sound waves, but it is there. But you can see how sound plays a role in our environment. So this will conclude our video on acoustics.